What if I told you that right now, at this very moment, there are things in our universe moving faster than light? What if Einstein's famous speed limit isn't quite as absolute as we've been taught? So what's going on here? Is everything we learned in physics class wrong? The truth is far more interesting and reveals the subtle ways our universe plays with its own rules. Today we're going to explore the real science behind faster-than-light phenomena, discover what can and can't break the light-speed barrier, and understand why the universe seems to have built-in loopholes in its most fundamental law. If you're curious about these cosmic mysteries, make sure to subscribe to this channel and give a thumbs up. Your support means a lot to me. One quick question: if you could travel faster than light for just one day, where in the universe would you go? Let me know in the comments down below. I will choose the most creative answer. Now let's begin. Let's start with the most mind-bending example: the expansion of space itself. Right now, there are galaxies moving away from us faster than the speed of light. The most distant galaxies we can see are currently about 46 billion light-years away, even though the universe is only 13.8 billion years old. How is this possible? The answer lies in understanding what the speed of light limit actually means. Einstein's rule says nothing can move through space faster than light, but space itself? That's a different story. Space can expand at any rate it wants, carrying galaxies along for the ride like raisins in rising bread dough. The galaxies aren't moving through space faster than light. Space itself is expanding between them. And by the way, if you're fascinated by the mysteries and controversies around the speed of light and want to go even deeper, I highly recommend the book called Faster Than the Speed of Light: The Story of a Scientific Speculation by Joel Magallo. It's a fascinating look at whether the universe's speed limit is truly unbreakable, or if there might be cosmic loopholes. The link of the book is in the description. This cosmic expansion was dramatically demonstrated during the period called inflation, which occurred in the first fraction of a second after the Big Bang. During inflation, the universe expanded by a factor of at least 10 to the 26th in just 10 to the negative 32 seconds. That's faster than light by an unimaginable margin. A region smaller than a proton became larger than a grapefruit almost instantaneously. The evidence for this faster-than-light expansion comes from the cosmic microwave background, mapped in exquisite detail by satellites like WMAP and Planck. These missions showed that opposite sides of the observable universe have nearly identical temperatures, which would be impossible unless they were once close enough to exchange information before inflation drove them apart faster than light. But cosmic expansion isn't the only way to beat light speed. Let's talk about quantum entanglement, what Einstein famously called spooky action at a distance. When two particles become entangled, measuring one instantly affects the other, no matter how far apart they are. This effect has been confirmed in countless experiments, with the 2022 Nobel Prize in Physics awarded to scientists who proved it beyond doubt. In 2015, researchers at the National Institute of Standards and Technology demonstrated quantum entanglement between particles separated by distances that light would take measurable time to traverse. Yet the correlation between the particles appeared instantaneous, at least 10,000 times faster than light speed. Some experiments suggest the effect might be truly instantaneous, representing infinite speed. Does this mean we can send information faster than light using quantum entanglement? Unfortunately, no. While the correlation is instantaneous, you can't use it to transmit useful information. It's like having two magic coins that always land on opposite sides, heads and tails, no matter how far apart they are. The correlation is real and instantaneous, but you can't control which coin shows heads, so you can't send a message. Another fascinating, faster-than-light phenomenon occurs in everyday materials. It's called Cherenkov radiation, and you might have seen it as the eerie blue glow in nuclear reactor pools. This happens when charged particles move through a medium faster than light travels in that medium. Wait, what? Particles moving faster than light? Here's the key: light slows down when it passes through materials like water or glass. In water, light travels at only 75% of its vacuum speed, but particles like electrons can zip through water at 90% the speed of light in vacuum, faster than light moves in that medium. When this happens, the particle creates a shock wave of light, similar to a sonic boom but with photons instead of sound. The Sudbury Neutrino Observatory in Canada uses this effect to detect neutrinos from the Sun. When a neutrino occasionally interacts with water molecules, it can create an electron moving faster than light in water, producing a flash of Cherenkov radiation. This technique has revealed fundamental truths about neutrinos and earned the 2015 Nobel Prize in Physics. Phase velocity provides another example of faster-than-light motion. When light waves pass through certain materials or waveguides, their phase velocity, the speed at which the wave crests move, can exceed the speed of light in vacuum. This has been demonstrated in laboratory experiments with specially designed metamaterials. In 2000, physicist Lijun Wang at NEC Research Institute in Princeton sent a pulse of light through a specially prepared cesium gas chamber. The pulse exited the chamber before it had finished entering. The peak of the pulse traveled at 310 times the speed of light in vacuum. This wasn't an error or illusion, it was confirmed by multiple detection systems. How is this possible without violating relativity? The key is that information still can't travel faster than light. While the wave peaks move superluminally, any actual information encoded in the light still propagates at or below light speed. It's like watching ocean waves from a pier. The pattern of waves might seem to move along the pier faster than the waves themselves are traveling, but you couldn't surf on that pattern. Quantum tunneling presents yet another puzzling case. When particles encounter barriers they shouldn't classically be able to cross, quantum mechanics allows them to tunnel through with some probability. Experiments have shown that the tunneling process itself might be instantaneous, regardless of barrier thickness. In 2020, researchers at the University of Toronto measured how long it takes for atoms to tunnel through optical barriers. Using ultra-precise atomic clocks, they found the tunneling time was consistent with 0. The atoms appeared on the other side instantaneously. This suggests that during tunneling, particles might temporarily exist outside the normal rules of space-time. The discoveries we've explored so far might make you think the universe is full of speed limit violations, like a cosmic highway where everyone's speeding, but the reality is more subtle and fascinating. The universe hasn't abandoned the speed of light limit, it's just revealed that this limit has very specific conditions and clever loopholes that nature exploits in surprising ways. Speaking of the speed of light limit, if you've ever wondered what would really happen if you could actually travel at light speed, I made a whole video breaking down the science, the mind-bending effects, and what you'd actually see on such a journey. After finishing this one, check out my video called What Would Really Happen If You Traveled at Light Speed. The link is in the description and on the card above. Let's dive deeper into one of the most spectacular examples: wormholes. These theoretical shortcuts through space-time could allow travel between distant regions of the universe without technically exceeding light speed. Imagine space-time as a piece of paper. Normally, you'd have to travel across the paper's surface to get from one point to another, but if you fold the paper so 2 points touch, you could step directly from one to the other, traveling a shorter distance without moving faster. The mathematics of general relativity, Einstein's theory of gravity, actually allows for wormholes to exist. The first solution was found by Ludwig Flamm in 1916, just 1 year after Einstein published his theory. Later, Einstein himself and Nathan Rosen explored these solutions, which is why wormholes are sometimes called Einstein-Rosen bridges. But here's the catch: every wormhole solution we've found requires exotic matter with negative energy density to keep it open. Without this exotic matter, a wormhole would collapse faster than light could traverse it. While quantum physics suggests negative energy densities are possible in tiny amounts, we see this in the Casimir effect between closely spaced metal plates. No one knows if enough exotic matter could exist to stabilize a human traversable wormhole. The Alcubierre drive presents another fascinating loophole. In 1994, physicist Miguel Alcubierre showed that Einstein's equations allow for a spacecraft to reach distant stars without locally exceeding light speed. The trick? Contract space in front of the ship and expand it behind, creating a warp bubble that carries the ship faster than light relative to distant observers. Inside the bubble, the spacecraft never exceeds light speed relative to its local space. It's like standing on a moving walkway at an airport. You're walking at normal speed, but the walkway carries you faster than someone walking on the stationary floor. Except in this case, space itself is the walkway. NASA's EagleWorks laboratory has actually studied the physics of warp drives. In 2012, physicist Harold White showed that the energy requirements for an Alcubierre drive might be reduced from impossible to merely impractical by changing the shape of the warp bubble. Instead of needing energy equivalent to Jupiter's mass, you might only need energy equivalent to the Voyager spacecraft's mass. But even these reduced requirements face fundamental problems. The Alcubierre drive still needs exotic matter, just like wormholes. It also creates causality paradoxes. In principle, you could use it to travel back in time, creating grandfather paradox scenarios. And recent calculations suggest the front of the warp bubble would accumulate deadly radiation that would fry anything at the destination when you stop. Tachyons represent another theoretical faster-than-light possibility. These hypothetical particles would always travel faster than light, just as regular particles always travel slower than light. The mathematics of special relativity doesn't forbid tachyons. It just says they could never slow down to light speed, just as regular matter can never speed up to it. If tachyons exist, they would have bizarre properties. Their mass would be described by imaginary numbers. They would travel backward in time from some reference frames, and, counterintuitively, they would speed up when they lose energy and slow down when they gain energy, opposite to normal particles. Despite decades of searching, no experiment has ever detected a tachyon. Particle accelerators, cosmic ray detectors, and astronomical observations have all come up empty. Most physicists now believe tachyons don't exist in nature, though they remain useful in certain theoretical calculations. The universe does seem to have a speed limit for information transfer, and this brings us to a profound realization. Every faster-than-light phenomenon we've discovered has a catch that prevents it from transmitting information faster than light. Quantum entanglement can't carry messages, phase velocities can exceed light speed, but information travels at the group velocity, which remains subluminal. Space can expand faster than light, but you can't use this expansion to send signals. This pattern suggests something deep about the nature of reality. The universe seems carefully constructed to prevent faster-than-light information transfer, even while allowing other things to exceed light speed. It's as if causality itself is more fundamental than the speed of light, and the speed limit exists to protect cause and effect relationships. Recent experiments have pushed these boundaries in fascinating ways. In 2011, the Opera experiment at CERN initially reported neutrinos traveling faster than light. The particles seemed to arrive at a detector in Italy 60 nanoseconds earlier than light would have. The announcement sent shockwaves through the physics community. For months, physicists scrutinized the experiment, proposed explanations, and ran independent tests. Eventually, two subtle errors were found: a loose fiber optic cable and a faulty clock. When corrected, the neutrinos were traveling at exactly the speed they should, just below light speed. The episode demonstrated both how seriously physicists take the speed limit and how carefully they verify any claims of breaking it. But the search continues with legitimate phenomena. In 2018, astronomers observed two neutron stars colliding, an event called GW170817. Both gravitational waves and light from the collision were detected, having traveled 130 million light-years to reach Earth. Remarkably, they arrived within seconds of each other, confirming that gravitational waves travel at light speed to incredible precision. This observation ruled out many alternative theories of gravity that predicted gravitational waves might travel faster or slower than light. It showed that the cosmic speed limit applies not just to matter and electromagnetic radiation, but to the very ripples in space-time itself. Cosmic inflation remains one of the most dramatic examples of apparent faster-than-light motion. During inflation, regions of space separated faster than light could travel between them. This explains one of the biggest mysteries in cosmology: why the universe looks so uniform in all directions. The cosmic microwave background temperature is nearly identical everywhere, varying by only 1 part in 100,000. Without inflation, opposite sides of the observable universe could never have been in causal contact to equilibrate their temperatures. Inflation solved this by proposing that these regions were once close together before being driven apart faster than light. The evidence for inflation has grown stronger with each new observation. The Planck satellite detected subtle patterns in the CMB that match inflation's predictions perfectly. The BICEP and Keck array experiments at the South Pole search for gravitational wave signatures from inflation, pushing our understanding of this faster-than-light epoch. But perhaps the most mind-bending aspect of faster-than-light phenomena involves the nature of space and time themselves. In general relativity, space and time aren't fixed stages where physics happens. They're dynamic, flexible parts of the universe that can bend, stretch, and even tear under extreme conditions. Near black holes, space-time becomes so warped that strange things happen. At the event horizon of a rotating black hole, space itself is dragged around faster than light relative to distant observers. This frame dragging effect has been measured around Earth by the Gravity Probe B satellite, confirming that massive objects really do drag space-time with them as they rotate. Inside a black hole's event horizon, the roles of space and time essentially switch. The radial direction becomes time-like, meaning falling toward the center becomes as inevitable as moving forward in time. Some theoretical solutions even suggest closed time-like curves, paths through space-time that loop back to their own past. While these probably don't exist in nature, they show how extreme space-time curvature can create apparent violations of our usual notions of speed and causality. When we dive into the quantum realm, our everyday understanding of speed and motion breaks down completely. At the smallest scales of reality, particles don't just travel from point A to point B like tiny bullets. Instead, they exist in a strange state of being potentially everywhere at once until we measure them. This quantum behavior reveals some of the most puzzling apparent violations of light speed limits and forces us to reconsider what we even mean by speed at the fundamental level. The double-slit experiment, first performed by Thomas Young in 1801 and later refined with individual particles, demonstrates this quantum weirdness perfectly. When electrons are fired one at a time at two parallel slits, something impossible happens. Each single electron somehow passes through both slits simultaneously and interferes with itself, creating an interference pattern on the detector screen. But here's where it gets even stranger. The electron doesn't just take both paths. Quantum mechanics says it takes every possible path between the source and the detector, including paths that loop around the universe before arriving. The probability of each path contributes to where the electron finally appears. Richard Feynman developed this sum over histories approach, showing that particles explore all possibilities faster than any classical speed limit would allow. Recent experiments have pushed this quantum behavior to extremes. In 2019, researchers at the University of Vienna demonstrated quantum superposition with molecules containing up to 2,000 atoms. These relatively massive objects existed in multiple places simultaneously, exploring different paths through their experimental apparatus in ways that would require faster-than-light coordination if we thought of them as classical objects. The quantum Zeno effect provides another example of how quantum mechanics seems to transcend normal speed limits. By repeatedly measuring a quantum system, you can freeze its evolution, preventing it from changing states. It's as if the universe has a pause button that works instantaneously across the entire quantum system, no matter how large it is. In 2015, researchers at Cornell University demonstrated this effect with atoms in an optical lattice. By frequently looking at the atoms with laser pulses, they could prevent the atoms from tunneling between lattice sites, a process that should happen naturally. The measurement itself, faster than any physical signal could propagate through the system, changed the behavior of the entire ensemble instantly. But the most dramatic challenge to light speed limits comes from quantum field theory, our most fundamental description of reality. In this framework, empty space isn't empty at all. It's seething with virtual particles that pop into existence and annihilate faster than the universe's speed limit should allow. These quantum fluctuations of the vacuum have real, measurable effects. The Casimir effect, where two metal plates in vacuum are pushed together by the pressure of virtual particles, has been measured precisely. The Lamb shift in hydrogen atoms, a tiny change in energy levels caused by virtual particles, was one of the first confirmations of quantum field theory and earned Willis Lamb the 1955 Nobel Prize in Physics. Virtual particles seem to violate everything we know about speed limits. They can have any speed, including faster than light. They can have negative energy. They can travel backward in time. But here's the crucial point. Virtual particles can't be directly observed. They exist only as intermediate states in quantum calculations, appearing and disappearing within the uncertainty principle's limits. The Heisenberg uncertainty principle itself creates a kind of speed limit loophole. It says that energy conservation can be violated for brief periods, with larger violations allowed for shorter times. During these fleeting moments, particles can borrow energy from the vacuum to do seemingly impossible things, including moving faster than light, as long as they pay back the energy debt quickly enough. This brings us to one of the most profound mysteries in quantum mechanics, the measurement problem. When we measure a quantum system, it instantaneously collapses from a superposition of many states to a single definite state. This collapse appears to happen faster than light across the entire system, no matter how large it is. In 2017, Chinese scientists demonstrated quantum entanglement between photons separated by over 1,200 kilometers using the Mitzius quantum satellite. When they measured one photon's polarization, its entangled partner's state was determined instantaneously, at least 10 million times faster than light could travel between them. This experiment extended previous ground-based tests to unprecedented distances, showing that quantum correlations don't weaken with distance. The delayed choice quantum eraser experiment adds another layer of weirdness. In this setup, the decision to measure or not measure certain quantum properties can seemingly change what happened in the past. Experiments at the University of Maryland have shown that choices made after a photon has passed through a double-slit apparatus can retroactively determine whether it went through one slit or both. This appears to send information backward in time, violating causality even more dramatically than exceeding light speed. But again, no usable information can be extracted from these correlations. The universe seems to have a built-in censorship mechanism that prevents these quantum effects from creating paradoxes. Quantum teleportation, despite its science fiction name, provides a real example of quantum information transfer. First achieved in 1997 by Anton Zeilinger's team in Austria, it allows the complete quantum state of a particle to be transmitted to a distant location. But even this process respects the speed of light in a subtle way. The teleportation requires both quantum entanglement and classical communication. While the entanglement correlation is instantaneous, you need to send classical information at light speed or slower to complete the teleportation. It's like having a locked box that opens instantly when someone far away turns a key, but you still need to tell them which way to turn it. Recent advances have made quantum teleportation increasingly practical. In 2020, researchers at Fermilab and other institutions demonstrated quantum teleportation over optical fiber networks with 90% fidelity. Chinese scientists have teleported quantum states from ground stations to satellites. These achievements bring us closer to a quantum internet, where information is processed in ways that classical physics would consider impossible. The many-worlds interpretation of quantum mechanics suggests an even more radical view of faster-than-light phenomena. In this interpretation, every quantum measurement causes the universe to split into multiple parallel realities. These splits propagate instantaneously throughout the universe, creating new branches of reality faster than light could carry the information. If many worlds is correct, then faster-than-light effects aren't just allowed. They're happening constantly as the universe branches into countless parallel versions. Every quantum event, from radioactive decay to photosynthesis in plants, creates new universes that diverge at infinite speed. We don't notice because we're confined to just one branch, unable to communicate with our parallel selves. Quantum computers exploit these quantum properties to perform calculations impossible for classical computers. They use superposition to explore many solutions simultaneously and entanglement to correlate information in ways that would require faster-than-light communication if done classically. Google's 2019 announcement of quantum supremacy demonstrated this power. Their Sycamore processor solved a specific problem in 200 seconds that would take classical supercomputers 10,000 years. While this doesn't violate speed limits directly, it shows how quantum mechanics allows information processing that transcends classical limitations. The quantum speed limit itself is a fascinating concept. In 2017, researchers at the University of Bonn showed that quantum systems have a fundamental maximum rate of evolution determined by their energy. This Margolis-Levitin theorem sets an absolute speed limit for quantum computation and any process involving quantum state changes, but even this quantum speed limit has surprises. Systems can evolve faster by becoming more entangled with their environment, effectively borrowing computational resources from the universe itself. It's as if the universe provides express lanes for quantum processes that classical physics can't access. As we venture beyond Earth and look into the cosmos, we find phenomena that make our previous examples seem almost mundane. The universe operates on scales where our intuitions about speed, distance, and time completely break down. From jets of plasma shooting out of black holes to the mysterious dark energy pushing galaxies apart, cosmic phenomena reveal just how creative nature can be in apparently circumventing its own speed limits. Let's start with one of the most spectacular displays in the universe, astrophysical jets. When matter falls into supermassive black holes at the centers of galaxies, it doesn't always disappear quietly. Instead, some of it gets redirected into narrow beams that shoot out from the black hole's poles at incredible speeds. These jets can extend for millions of light years, carrying energy and matter far beyond their host galaxies. Here's where things get weird. When astronomers observe these jets over time, they sometimes see individual bright spots, called knots, that appear to move across the sky faster than light. This superluminal motion has been observed in dozens of jets, with some appearing to move at 10 times light speed or more. The first discovery of this effect came in 1971 when astronomers observed the quasar 3C279. They saw components of its jet separate at a rate that implied speeds of 10 times the speed of light. This caused a crisis in astronomy. Were we seeing actual faster-than-light motion, or was something else going on? The answer turns out to be a clever trick of perspective. These jets are moving at speeds very close to light speed, typically 99% or more, and they're aimed almost directly at us. This creates an optical illusion where the jet appears to move sideways across our sky faster than light, even though it's actually moving just below light speed at a small angle to our line of sight. Think of it this way. Imagine a car driving toward you at night with its headlights on. If the car is moving at nearly light speed and aimed slightly off to your side, the light it emits from different positions bunches up, making it appear to zip sideways impossibly fast. The math works out so that a jet moving at 99.9% light speed at an angle of about 5 degrees to our line of sight would appear to move at 7 times light speed across the sky. The Very Long Baseline Array and other radio telescope networks have now mapped hundreds of these superluminal jets. Some of the most extreme examples, like those in the galaxy M87, famous for the first black hole image, show apparent speeds up to 6 times light speed. These observations have actually helped us measure the real speeds of the jets and understand the physics of how black holes can accelerate matter to such extreme velocities. But jets aren't the only cosmic light-speed mystery. Gamma-ray bursts, the most energetic explosions in the universe since the Big Bang, present their own puzzles. These events release more energy in seconds than our Sun will produce in its entire 10 billion-year lifetime, and they do it from regions just a few kilometers across. The problem is that such a small region shouldn't be able to coordinate such a massive energy release. Different parts of the exploding region are too far apart for light signals to coordinate their activity, yet somehow the entire region explodes in perfect synchronization. This is called the compactness problem, and it suggests that something faster than light coordinates the explosion. Recent observations by the Fermi Gamma Ray Space Telescope have made this mystery even deeper. Some gamma-ray bursts show variability on timescales of milliseconds, implying the emitting region is just a few hundred kilometers across. Yet these tiny regions produce focused jets that maintain their coherence for thousands of light years. How does nature achieve such precise coordination? One solution might involve quantum effects on macroscopic scales. Some theorists propose that extreme conditions in gamma-ray bursts could create quantum coherence across the entire exploding region, allowing instantaneous coordination through entanglement-like effects. While speculative, this would represent quantum mechanics operating on astrophysical scales. Dark energy presents perhaps the ultimate cosmic speed mystery. This mysterious force, which makes up about 68% of the universe's energy density, is causing cosmic expansion to accelerate. As we look at more distant galaxies, we see them receding faster and faster with no apparent limit. The Hubble Space Telescope's observations of type Ia supernovae first revealed this acceleration in 1998. More recent observations by the Dark Energy Survey and other projects have mapped this acceleration in exquisite detail. The results are unambiguous. Galaxies are accelerating away from each other, and given enough time, they will exceed light speed relative to us. In fact, this is already happening. Galaxies more than about 14 billion light-years away are currently receding faster than light due to cosmic expansion. We can still see them because we're seeing light they emitted billions of years ago when they were closer and moving slower. But light they're emitting right now will never reach us. They've passed beyond our cosmic event horizon. This creates a profound realization. The observable universe is shrinking even as the actual universe expands. Every second, about 20,000 stars pass beyond our cosmic event horizon, becoming forever unobservable. In the far future, perhaps 100 billion years from now, all galaxies beyond our local group will have disappeared beyond this horizon, leaving us apparently alone in the universe. The cosmic web, the largest structure in the universe, also displays apparent faster-than-light coordination. Galaxies are arranged in vast filaments and walls separated by enormous voids, creating a pattern that spans billions of light-years. Computer simulations show this structure forming through gravitational attraction, but the largest features seem too big to have formed in the available time without some form of faster-than-light coordination. The Boss Great Wall, discovered in 2016, stretches over 1 billion light-years across. For a structure this large to form through normal gravitational attraction would require communication between its distant parts. Yet the structure is so large that light hasn't had time to travel from one end to the other since the Big Bang. How did distant regions know to form part of the same structure? The answer might lie in the early universe. During cosmic inflation, regions that are now billions of light-years apart were once microscopically close. Quantum fluctuations in this tiny region were stretched to cosmic scales by inflation, seeding the patterns we see today. In a sense, the cosmic web structure was determined by faster-than-light expansion in the universe's first fraction of a second. Observations by the Sloan Digital Sky Survey have mapped millions of galaxies, revealing the cosmic web in unprecedented detail. These maps show that the largest structures in the universe push against theoretical limits for how large gravitationally bound structures can be. Some features, like the Hercules Corona Borealis Great Wall, are so large they challenge our understanding of structure formation. Fast radio bursts add another layer to cosmic speed mysteries. These millisecond duration pulses of radio waves come from distant galaxies, releasing as much energy in milliseconds as the Sun emits in days. First discovered in 2007, hundreds are now known, with some repeating unpredictably. The challenge is explaining how such brief, energetic events can be produced. The emitting region must be smaller than a few hundred kilometers. The distance light travels in a millisecond, yet it must coordinate the coherent emission of enormous amounts of radio waves. Some models invoke relativistic shock waves or magnetic field reconfigurations that happen faster than light can cross the emitting region. CHIME, the Canadian Hydrogen Intensity Mapping Experiment, now detects multiple fast radio bursts daily. Some show complex structure with sub-microsecond features, implying even smaller emission regions. The more precisely we measure these events, the harder they become to explain without invoking extreme physics that pushes against light speed limits. To truly understand the speed of light limit and its apparent violations, we need to examine the nature of space-time itself. What we call empty space is far from empty. It's a dynamic, quantum mechanical entity with its own properties and behaviors. At the smallest scales and highest energies, space-time might not even be continuous, and this graininess could allow for phenomena that seem to violate our usual understanding of speed limits. The Planck scale represents the frontier where our current physics breaks down. At distances of about 10 to the negative 35 meters, that's a decimal point followed by 34 zeros and then a 1, space and time lose their meaning as smooth, continuous entities. At this scale, quantum fluctuations of space-time itself become so violent that the very concepts of distance and duration become uncertain. To put this in perspective, if an atom were enlarged to the size of the solar system, the Planck length would still be smaller than a grain of sand. At these impossibly tiny scales, virtual black holes pop into existence and evaporate in about 10 to the negative 43 seconds, the Planck time. During their brief existence, these quantum black holes could connect distant regions of space, creating microscopic wormholes that appear and disappear faster than light could traverse them. Loop quantum gravity, one approach to unifying quantum mechanics, and general relativity, suggests that space-time has a discrete structure at the Planck scale. Space would be made of tiny loops or networks like a fabric woven from incredibly fine thread. In this picture, motion through space would be like moving across a grid, jumping from one discrete point to another rather than moving smoothly. This discreteness could allow for interesting loopholes in the speed limit. Information might be able to skip across the quantum foam through connections that don't exist in our smooth, large-scale view of space-time. Some theorists have proposed that quantum gravity effects could allow signals to take shortcuts through the Planck scale structure, effectively traveling faster than light on large scales while never exceeding light speed locally. String theory offers another perspective on space-time's fundamental nature. In this framework, what we perceive as particles are actually tiny vibrating strings in a 10 or 11-dimensional space-time. The extra dimensions are compactified, rolled up so small we can't detect them directly. But these hidden dimensions might provide pathways for faster-than-light phenomena. In some string theory models, our three-dimensional space is like a membrane floating in a higher dimensional bulk. Gravity can propagate through the bulk, potentially taking shortcuts unavailable to matter, and light confined to our membrane. This could explain why gravity appears weaker than other forces. It's diluted by spreading into extra dimensions. Recent experiments have searched for signs of these extra dimensions. The Large Hadron Collider looks for missing energy that could indicate particles escaping into the bulk. Tabletop experiments test whether gravity deviates from Newton's law at sub-millimeter distances. So far, no evidence for extra dimensions has been found, but the search continues with ever-increasing precision. Black holes provide natural laboratories for testing the limits of space-time. At their event horizons, space and time become so distorted that our usual concepts break down. Inside the horizon, space flows like a river toward the singularity, and this flow exceeds light speed. This is why nothing can escape. You'd have to swim upstream faster than light to get out. But black holes might not be the one-way traps we thought. Stephen Hawking's discovery of black hole evaporation through quantum effects suggests information can escape, albeit in a highly scrambled form. This process involves virtual particle pairs created near the horizon, with one falling in and the other escaping. The escaping particle appears to have traveled from inside the horizon, a seemingly impossible feat. Recent work on the black hole information paradox has led to even stranger proposals. The ER-EPR conjecture suggests that quantum entanglement between particles might be equivalent to microscopic wormholes connecting them. If true, every entangled pair in the universe would be connected by a tiny Einstein-Rosen bridge, creating a vast network of faster-than-light connections at the quantum level. The holographic principle adds another layer to this mystery. It suggests that all the information in a volume of space can be encoded on its boundary, like a hologram. For black holes, this means all the information about what fell in is somehow stored on the two-dimensional event horizon. This dimensional reduction might allow for information processing that appears to violate bulk speed limits while respecting them on the boundary. Cosmological horizons present similar puzzles. Our observable universe has a boundary and the cosmic event horizon, beyond which we cannot see or influence anything. But inflation theory suggests our observable universe is just one bubble in an infinite multiverse. Other bubbles might have different physical constants, including different speed limits for light. In eternal inflation models, new universes are constantly being created as different regions of space stop inflating at different times. These universes would be completely disconnected from each other, separated by regions still undergoing exponential expansion. The speed of light might be different in each universe, determined by random quantum fluctuations during their birth. Some physicists have proposed that the speed of light might not be constant even within our universe. Variable speed of light theories suggest C might have been different in the early universe, potentially solving some cosmological puzzles without invoking inflation. João Magalhães and Andreas Albrecht proposed that light might have traveled much faster in the hot, dense, early universe, allowing distant regions to communicate and equilibrate. While observations tightly constrain any variation in C today, the early universe might have been different. Some models suggest the speed of light could have been infinite at the Big Bang, decreasing to its current value as the universe cooled. This would naturally explain the universe's large-scale uniformity without requiring inflation's faster-than-light expansion. Quantum gravity phenomenology, the study of how quantum gravity effects might appear in experiments, has identified several possible signatures of spacetime's fundamental structure. These include modifications to how light of different energies travels through space, violations of Lorentz invariance, and changes in how particles behave at extreme energies. The MAGIC telescope has searched for these effects by observing gamma rays from distant cosmic events. If space-time is grainy at the Planck scale, high-energy photons might travel slightly slower than low-energy ones, accumulating a measurable delay over billions of light-years. So far, no such delay has been detected, placing tight constraints on quantum gravity theories. Gravitational waves offer a new window into spacetime's fundamental nature. LIGO and Virgo have detected ripples in spacetime from colliding black holes and neutron stars. These observations confirm that gravitational waves travel at exactly light speed, ruling out many alternative theories of gravity that predicted different speeds. Future detectors like LISA will observe gravitational waves from supermassive black holes, probing even more extreme conditions. The proposed Einstein telescope could detect quantum corrections to gravitational wave signals, potentially revealing how spacetime behaves at its most fundamental level. The possibility of spacetime emergent from something more fundamental has gained traction recently. In this view, space, time, and the speed of light limit aren't fundamental but arise from deeper quantum mechanical structures. Just as temperature emerges from molecular motion, spacetime might emerge from entanglement patterns in a more fundamental quantum system. While cosmic phenomena give us natural experiments in extreme physics, scientists aren't content to just observe. They're actively creating conditions in laboratories that probe and seemingly bend the universal speed limit. From particle accelerators that push matter to 99.99999% the speed of light, to quantum experiments that seem to send information backward in time, these controlled studies are revealing just how subtle and strange the universe's speed rules really are. The Large Hadron Collider at CERN is humanity's most powerful probe of nature's speed limits. This 27-kilometer ring accelerates protons to energies of 7 trillion electron volts, reaching speeds where relativistic effects become extreme. At these velocities, time dilation is so severe that 1 second for the proton equals about 7,000 seconds for us watching from the lab. But here's what's truly mind-bending. Despite pumping enormous energies into these particles, we can never quite push them to light speed. Each additional decimal place of precision towards C requires exponentially more energy. The LHC uses enough electricity to power a small city, yet the protons still fall short of light speed by about 3 meters per second, the speed of a jogging human. The particles in the LHC experience forces that would seem to violate everyday physics. They're bent around curves by magnetic fields so strong that if the particles were traveling any slower, they'd be torn apart. The fact that they survive these forces is due to relativistic effects. At near-light speeds, the electromagnetic forces that hold particles together are enhanced in precisely the right way to maintain their integrity. Recent experiments at the LHC have produced quark-gluon plasma, a state of matter that existed in the first microseconds after the Big Bang. In this exotic substance, quarks and gluons move freely rather than being confined in protons and neutrons. The plasma appears to flow as a nearly perfect liquid with almost zero viscosity, allowing disturbances to propagate at speeds approaching the theoretical maximum allowed by relativity. But particle accelerators have revealed something even stranger. Particles that travel faster than light in a medium can go backward in time, at least from certain perspectives. When charged particles exceed light's speed in a material, remember, this is possible because light slows down in media. They emit Cherenkov radiation. From the particle's reference frame, this radiation appears to be emitted backward in time, creating a causal paradox that's resolved only through careful application of relativity. Laser physics provides another arena for speed limit experiments. Scientists have created pulses of light that appear to travel faster than C in vacuum. In 2000, Lijun Wang's team at NEC Research Institute sent a light pulse through a specially prepared cesium chamber where it exited before it finished entering, achieving an effective speed of 310 times c. The key to this seeming impossibility lies in the difference between phase velocity, group velocity, and signal velocity. While the peak of the light pulse traveled faster than c, no information actually exceeded light speed. It's like a wave pattern that moves along a beach faster than the individual waves. The pattern moves quickly, but you couldn't surf on it to exceed the wave speed. More recently, scientists have stopped light completely. In 2013, researchers at the University of Darmstadt trapped light in a crystal for over 60 seconds. They encoded information in the light, stopped it, held it in the crystal's atomic structure, then released it on command. While stopped, the light essentially didn't exist as light. It was stored as a quantum excitation in the crystal's atoms. This technique, called electromagnetically induced transparency, has profound implications. If we can stop and store light, we can manipulate it in ways that seem to violate our usual understanding of electromagnetic radiation. Some researchers have proposed using stopped light to create time crystals, structures that repeat in time rather than space, potentially allowing information to loop through time in controlled ways. Metamaterials, artificial structures with properties not found in nature, have opened new possibilities for manipulating light speed. Scientists have created materials with negative refractive indexes, where light bends the opposite way from normal when entering the material. In these materials, phase velocity and group velocity point in opposite directions, creating regions where light appears to flow backward. In 2006, researchers at Duke University created the first invisibility cloak using metamaterials. While not perfect, it demonstrated that we can guide light around objects in ways that seem to violate normal physics. Some theoretical proposals suggest metamaterials could create space-time cloaks that hide events in both space and time, creating gaps in history that light cannot reveal. Quantum experiments have pushed even harder against speed limits. The quantum Cheshire cat effect, demonstrated in 2014 at the Vienna University of Technology, separated a neutron from its magnetic moment, like separating a grin from a cat in Alice in Wonderland. The neutron went through one path while its magnetic property went through another, requiring instantaneous coordination that classical physics can't explain. Interaction-free measurements represent another quantum paradox. Scientists can determine if an object is present without any particle or wave actually interacting with it. The Elitzur-Vaidman bomb tester, demonstrated experimentally in 1994, can determine if a bomb is live without triggering it, using quantum interference effects that seem to require faster-than-light coordination. The quantum Zeno effect has been pushed to extremes in recent experiments. By measuring a quantum system frequently enough, scientists can completely freeze its evolution. In 2015, researchers at Washington University demonstrated that they could keep an atom in an excited state indefinitely by measuring it often enough, preventing it from decaying through what amounts to quantum surveillance. But perhaps the most startling experiments involve retrocausality, the possibility that future measurements can influence past events. The delayed choice quantum eraser, refined in numerous experiments since 2000, shows that decisions about what to measure can retroactively determine what happened earlier in the experiment. In 2017, researchers at the University of Queensland demonstrated this effect with single photons, showing that the choice to measure or not measure wave-like properties could retroactively determine whether the photon had traveled as a wave or particle. The effect is real and reproducible, though it can't be used to send information to the past due to quantum uncertainty. Superluminal tunneling continues to puzzle physicists. When particles encounter barriers they shouldn't classically be able to cross, quantum mechanics allows them to tunnel through with some probability. Recent experiments with ultra-cold atoms have shown that this tunneling process might be instantaneous, regardless of barrier width. In 2020, researchers at the University of Toronto measured tunneling times with unprecedented precision using attosecond laser pulses. They found the tunneling time was consistent with zero. Particles appeared on the other side of barriers instantaneously. This suggests that during tunneling, particles might temporarily exist outside normal space-time. Scientists are also exploring whether quantum effects could allow faster-than-light communication through proper measurement strategies. While the no-communication theorem supposedly forbids this, researchers continue to find loopholes and edge cases. Some proposals involve post-selection, where only certain measurement outcomes are kept, potentially allowing superluminal signaling in carefully controlled conditions. The quest to understand and possibly circumvent light speed limits has led to increasingly exotic experiments. Scientists have proposed using the Casimir effect to create regions of negative energy density, potentially stabilizing microscopic wormholes. Others are exploring whether quantum computers might process information in ways that effectively exceed classical speed limits, even if they don't violate relativity directly. After exploring all these phenomena that seem to challenge the speed of light limit, from quantum entanglement to cosmic expansion, from laboratory experiments to black hole physics, we arrive at a profound realization. The universe hasn't actually broken its own rules. Instead, it's revealed that the rules are far more subtle, beautiful, and strange than we ever imagined. The speed of light isn't just a speed limit, it's a fundamental feature that shapes reality itself, and understanding its true nature changes everything about how we see our place in the cosmos. Let's step back and consider what we've really discovered. Yes, space itself can expand faster than light, carrying galaxies beyond our cosmic horizon. Yes, quantum particles can correlate instantaneously across any distance. Yes, we can make light pulses that appear to travel faster than C in certain media. But in every single case, there's a catch that preserves the deeper principle. Causality itself cannot be violated. Information, energy, and causal influence remain locked below the speed of light. This isn't a coincidence or a cosmic conspiracy. It reflects something fundamental about the nature of existence. The speed of light is better understood not as a speed limit for objects, but as the maximum rate at which cause and effect can propagate through space-time. It's the speed of causality itself, the rate at which one event can influence another. Light just happens to travel at this speed because photons are massless. They're riding the cosmic speed limit because nothing is holding them back. Think about what would happen if this limit didn't exist. If information could travel infinitely fast, the entire universe would be in instantaneous contact with itself. Every event, everywhere, would immediately affect everything else. There would be no isolation, no independent systems, no time for causes to lead to effects. The universe would be a frozen crystal of instantaneous correlations rather than the dynamic, evolving cosmos we observe. Even more fundamentally, faster-than-light travel would break the relationship between cause and effect. Thanks to Einstein's relativity, we know that observers moving at different speeds disagree about the simultaneity of events. What appears simultaneous to you might appear sequential to someone moving relative to you. If faster-than-light travel were possible, you could send signals into your own past, creating grandfather paradoxes that would make logical existence impossible. The universe seems carefully designed to prevent these paradoxes. Every loophole that might allow faster-than-light effects comes with a built-in protection mechanism. Quantum entanglement can't carry usable information. Wormholes require exotic matter that probably doesn't exist. Cosmic expansion can exceed light speed, but it can't be used for communication. It's as if reality has multiple backup systems to ensure causality is never violated. This has profound implications for our future as a species. The dream of Star Trek-style faster-than-light travel, where we zip between stars in days or weeks, appears to be forever impossible. The universe is telling us that if we want to explore the stars, we'll have to do it the slow way, taking years, decades, or centuries to reach even the nearest stellar systems. But this limitation might actually be a gift. If faster-than-light travel were easy, the galaxy would probably already be colonized by older civilizations. The fact that we see no evidence of this, the famous Fermi paradox, might be explained by the absolute nature of the light-speed barrier. Every civilization, no matter how advanced, faces the same cosmic speed limit. This forces us to think differently about our cosmic future. Instead of quick jaunts between stars, we might need generation ships, vast arcs that support human populations for centuries as they slowly travel to other systems. Or we might send robotic probes that can handle the long journey times, establishing infrastructure before humans arrive. Or we might turn to radical life extension or suspended animation to make the journey times bearable. The light speed limit also shapes how we might communicate with other civilizations. Any conversation with beings around other stars would involve years or decades between messages. We couldn't have real-time dialogue. Instead, we'd exchange long, detailed messages, each one a careful composition meant to convey as much as possible. It would be less like a phone call and more like exchanging books, but perhaps the most profound implication is philosophical. The speed of light limit means we're fundamentally isolated in space-time. Each observer exists in their own light cone, able to influence only events in their future light cone and be influenced only by events in their past light cone. We're all islands of causality in the vast ocean of space-time. Yet this isolation is what makes existence meaningful. Because effects take time to propagate, we have time to think, to choose, to act. The delay between cause and effect is what allows complex structures like atoms, molecules, and life to exist. If everything happened instantaneously, there would be no process, no growth, no evolution, just static being. The speed of light limit also ensures that the universe has a history. Because information takes time to travel, we can look back in time by looking out in space. Every telescope is a time machine, showing us the universe as it was, not as it is. This cosmic archaeology allows us to piece together the story of existence, from the Big Bang to the present. Consider how remarkable this is. When you look at the Andromeda Galaxy, you're seeing it as it was 2.5 million years ago. The light entering your eyes is older than our species. You're directly observing the deep past, receiving ancient photons that have traveled across the cosmic void to tell you their story. The universe's speed limit has turned the night sky into a vast historical record. Looking forward, the accelerating expansion of the universe means that the speed of light limit will become even more isolating. Billions of years from now, galaxies will be so far apart that their light can no longer reach each other. Each galaxy will become its own island universe, surrounded by absolute darkness. The cosmic web will dissolve into disconnected fragments, each forever alone. But we live in a special time, perhaps the only time in the universe's history when we can see both its beginning and glimpse its future. We can detect the cosmic microwave background from the Big Bang and observe the accelerating expansion that foretells the universe's fate. Future civilizations won't have access to this information. The evidence of the Big Bang will be redshifted beyond detection, and other galaxies will have vanished beyond the cosmic horizon. This makes our scientific discoveries not just important for us, but for any future intelligence in our galaxy. We're the universe's historians, recording its story while the evidence is still visible. The knowledge we gather about cosmology, about the speed of light and its implications, might be the only record that survives into the far future. The universality of the speed of light also means that any alien civilization, no matter how different from us, must have discovered the same limit. The speed of light is a universal constant that all intelligent beings must recognize. In a sense, c equals 299,792,458 meters per second is a piece of knowledge we share with any possible alien intelligence. It's a cosmic common ground. As we stand on Earth, looking up at the stars, we're seeing the universe through the lens of its ultimate speed limit. Every point of light is a message from the past, every galaxy a time capsule. The speed of light has isolated us in space and time, but it's also connected us to the cosmic story. We're made of atoms forged in stars whose light is just now reaching distant galaxies. We're part of a vast, slow cosmic dance where every step is limited by c, but where the pattern that emerges is beautiful beyond imagination. The speed of light limit isn't a barrier to overcome, it's a fundamental feature that makes our universe possible. It ensures causality, enables complexity, and gives meaning to space and time. While we may never travel faster than light, understanding why reveals something even more valuable: our deep connection to the cosmos and our special moment in its vast history. We are the universe understanding itself, and the speed of light is the pace at which that understanding can spread. If you are still watching, please consider subscribing and giving a thumbs up. And if you enjoyed this video, I am sure you will love this one at the left side of the screen. What would happen if we could travel faster than light? In this video, discover the mind-blowing science and consequences of breaking the cosmic speed limit. Explore how faster-than-light travel would transform space exploration, time, and the future of humanity. See you there.